Hi, I'm Robert Rojas. In this video, I will demonstrate to you how the Hidden Markov Model, or HMM, works using the Viterbi algorithm. Sample computations using a super tiny corpus containing 10 sentences and our simple tag set will be presented. If you have not watched the previous video titled Hidden Markov Models, I encourage you to watch that video from the same computer science lecture notes channel. We will be using the HMM components that we have built in that demonstration video. Let's start now. Given a hidden Markov model lambda containing the parameters A and B, where A is the transition probability and B is the emission probability respectively, and a sequence of observations O from O sub 1 to O sub t, find the most probable sequence of states Q, Q sub 1 to Q sub t. In natural language processing, the sequence of observations is the input string or the individual words of the input sentence. The resulting sequence of states is the corresponding part of speech tags of the input sentence. The same as with solving the likelihood problem, using a brute force approach to maximize the probability of each possible hidden state sequences n raised to the power t is intractable. The Viterbi algorithm is a dynamic programming algorithm. In determining the best sequence of states, the algorithm requires the use of back pointers to track the path of the hidden states. The algorithm only runs in O of n squared times t. The Viterbi algorithm requires the use of an n by t table to store the values involved in the computation. Each cell, alpha sub t q, where small t is less than or equal to capital T, shall denote the probability of the word O sub t having the state q. For example, to find the correct sequence of the tags for the sentence, Christ healed the blind, a matrix like the one shown on the screen should be created first. Please note that this is just a partial table for illustration purposes only. The actual table will be very large if all tags are included. The example is limited to a few POS tags that are needed in illustrating the example. Of course, for illustration purposes, an additional tag which is not needed in the computation is used also. In our example, the PRN tag is not used in the sentence. This is done so that it can be seen that other tags that are not needed in the computation do not affect the result. In the Viterbi algorithm, we have 3 steps to follow. That is the initial step, the recursion step, and the termination step. Each of these steps will be illustrated in a while. Each step has its own formula, and we will illustrate it with a simple running example. Let's start now with the initial step. Let's fill in the first column of the table using the formula shown on the screen. The formula states that the value of cell V sub 1j is just the transition probability from state 0 to state j times the emission probability at state j. This will be illustrated in a while. The back pointers for the initial states are all set to 0, denoting the start hidden state. Let us compute for the most likely tag for the word Christ that starts the sentence, Christ healed the blind. Let's start with the PRN tag. The probability of Christ following the start marker is equal to the transition probability of PRN following the start marker times the emission probability of Christ associated with PRN. Based on the graph, the transition probability of PRN that follows the start marker is 0.1. But the emission probability of Christ associated with PRN is 0. The same process is applied to other tags like VTR and det. But let me illustrate the computation for the in tag for nouns. The probability of Christ following the start marker is equal to the transition probability of noun following the start marker times the emission probability of Christ associated with n. Based on the graph, the transition probability of n following the start marker is 0.6 and the emission probability of Christ associated with n is 0.158. So, the probability of Christ following the start marker is 0.0948. We can now store these computed values into the n by t table as shown on the screen. Although only one has a non-zero value, it does not mean that it will always be the case that only the winning probability has the non-zero value. It just happened that our super tiny corpus has a very limited number of stored sentences. In reality, non-zero values can appear in any of the slots. The result of the computation can also be graphically visualized as a transition graph, just like the one shown in the screen. In the transition graph, the formulas are shown in the arcs. The arc that points to the winning tag is shown in red for easy viewing. Let's now move to the recursion step. For each succeeding cells B sub t with parameter j in the table, the probabilities are computed as the result of computing the maximum probability of transitioning from the previous state to the current state. The formula is shown on the screen, where it is just the value of the state I times the transition probability from state I to state j times the emission probability of observation t at state j. Then, after computing the maximum probabilities of coming from a given tag to another tag, the overall maximum will be taken using the formula shown on the screen as the back pointer. Let us now compute for the most likely tag for the word healed as the second word of the sentence, Christ healed the blind. The probability of healed associated with PRN is 0 because all products are zeros. The probability of healed associated with VTR has a non-zero value resulting from the probability of the previous word, Christ, associated with the in tag, which is 0.0948 times the transition probability of 0.21 times the emission probability of 0.2, which is equal to 0.00398. The probability of healed associated with death is 0 because all products are zeros. And the same is true for the probability of healed associated with n. So the resulting table looks like the one shown on the screen. And the back pointer is the maximum of the previous column, that is for the word Christ. The corresponding transition graph is shown on the screen, and the back pointer is indicated by a blue back arrow. Please note that what is illustrated in the transition graph as shown on the screen is just the computation of the probability of healed associated with VTR, which has the highest probability among the 4 tags. This is done to avoid cluttering the figure with so many arrows with labels. Let us now compute for the most likely tag for the word the of the sentence, Christ healed the blind. The probability of the associated with PRN and the probability of the associated with VTR are zeros because all their products are zeros. The probability of the associated with death is 0.00398 times 0.8 times 0.917, which is equal to 0.00292, being the maximum among the 4 computed values. The probability of the associated with n is 0 because all products are zeros. The resulting table is shown on the screen, and its corresponding transition graph is shown on the screen. Let us now compute the most likely tag for the word blind as the last word in the sentence, Christ healed the blind. The probability of blind associated with PRN, the probability of blind associated with VTR, and the probability of blind associated with death are all zeros because all their products are zeros. The probability of blind associated with n is 0.00292 times 0.92 times 0.053, which is equal to 0.00014, being the maximum among the 4 computed values. The resulting table is shown on the screen, and its corresponding transition graph is shown on the screen. Let's now move to the termination step. The termination step uses the max function instead of summation to determine the best state sequence. It uses the formula that is shown on the screen. It gives the maximum of the products of the value of state I times the transition probability to the final state. Let us compute for the most likely tag that connects to the end marker state. Since the last word in the sentence is blind, the probability of the end marker following the blind is computed. The word blind is a noun, which has a previously computed value of 0.00014. This value is multiplied by the transition probability of the end marker associated with n, which is 0.37, which is equal to 0.0000518, being the maximum among the 4 computed values. The resulting transition graph is shown in the screen. So, we have successfully computed all the necessary computations. The final result is visually displayed as shown in the screen. If we trace the back pointer as shown in the screen, we can see the path going back to the tag of the first word of the sentence. If we view it graphically by following the red arrow, we can clearly see the sequence of tags for the sentence Christ healed the blind. If we follow the red arrow, we can get to the tag sequence N, VTR, death, N, which is the correct tag sequence. Therefore, the HMM tagger has successfully and correctly tagged the sentence Christ healed the blind, even though there is no matching sentence in the super tiny corpus that we used. In other words, it learns from the existing tagged corpus. Thank you very much. I hope these lecture notes in audiovisual form have helped you in some way in understanding how the hidden Markov model works in your computer science journey. Bye.